Practice Exam 2, Problem 1. A. Light refracts from material 1 into a thin layer of material 2, crosses that layer, and then is incident at the critical angle on the interface between materials 2 and 3, and refracts into material 4. I. What is the angle theta of refraction into material 4? I. Draw an accurate diagram of the situation, and if theta is decreased, is there refraction of light into material 3? Explain your reasoning. I will first start off by drawing an accurate ray diagram of the refractions and reflections for this part. So I first draw in my normal. I label this first point A, and this is the angle that the ray would go in if there was no change of index of refraction between 1 and 2. So now, since I'm going from a lower to a higher, the ray bends towards the normal. So now I see the refraction. At the boundary between 2 and 3, there's critical reflection. Let's write in those details. So I label this angle theta 2, and I know that this is critical. After the internal reflection, I go to point B. Now note that I'm going from medium 2 to medium 4. I go from a higher to a lower, so then the ray bends away from the normal. So let's label these two angles. I'm calling this angle then theta 2 prime, and I'm calling this angle theta 4. That's an accurate ray diagram. To determine this angle theta, I must first determine the critical angle theta c. From Snell's law of refraction, I could see here that the light coming from 2 is going to be n2 sine of theta critical, and then the refracted angle is along the boundary here, which is n3 sine of 90. That implies that the critical angle is then the sine inverse of the ratios of these index of refractions. Now that we have theta critical, we can solve for the angle theta 2 by summing internal angles of a triangle. In other words, the sum of these angles must be 180. When we do this, we get an angle of 43.8 degrees for theta 2. If we now apply Snell's law of refraction at point A here, we get that n1 of this angle is equal to n2 of sine of theta 2. So if I do the algebra, I then get that theta is equal to the sine inverse of n2 sine theta 2 divided by n1. Plugging in the numbers, we get theta is equal to 51.1 degrees. B. Unpolarized light with an intensity of 25 watts per meter squared is sent into a system of 4 polarizing sheets with polarizing directions at angles theta 1, 40 degrees, theta 2, 20 degrees, theta 3, 20 degrees, and theta 4 equal to 30 degrees. Draw an accurate polarization vectors for this situation. What is the intensity of the light that emerges from the system? Let's start by drawing an accurate polarization diagram of the polarization vectors. I have incident, unpolarized light with intensity I0 going along this diagram. The problem is that this is very hard to interpret, so we want to redraw the polarizers to make it more clear. So now I have my 4 polarizers, I have my unpolarized light, and I put down the angles given, and we need to then translate these angles there. Let's start putting in the angles. So if I look at the first one, theta 1, note that it's 40 degrees from the vertical. Here's 40 degrees, so the polarizer looks like this. Now let's go look at the second one. The second one is at theta 2 from the horizontal. So there's my theta 2, which is 20 degrees. Let's draw that in. Look at theta 3 now, and it's 20 degrees from the horizontal in this direction. So it looks like this. Finally, the fourth polarizer, theta 4, you could see that it's measured from the vertical, but note that this angle is the same as the angle up here, which then gives me that 30 degrees there. Now I put in all the angles of the polarizers. Let's go in and start to look at the polarization vectors. So for the first polarizer, we know that we're going to get half the light coming through, and the polarization vector is going to be perpendicular to this axis. Now I have I1 with this polarization. Now the light that comes out of here is going to be perpendicular to that. It's going to look roughly like this. So now I have intensity I2. So then I do the same thing for 3. Then finally, I get the fourth polarizer, which gives me this polarization vector. The intensities are the angle differences between the two adjacent polarizers. So when I look at the intensity at 4, it's the angle difference between these two that matters. That is, the intensity I4 is I4 equal to I3 times cosine squared, the difference between the angles 3 and 4. So this delta theta 3, 4 then, if I look at the fourth polarizer at 30 degrees, the third polarizer at 20 degrees, then that means that difference must be 40 degrees. So now I have intensity 4 as a function of intensity 3 times cosine squared of 40 degrees. Let's go get intensity 3. So I3 is equal to I2 cosine squared of delta theta 2, 3. Let's look at the angles. So that means here that if I look at the third polarizer, you could see that in orange here I got 20 degrees. If I look at the second polarizer, note that that's 20 degrees here, but that means that it's I could also draw the angle by this green 20. The angle difference between 2 and 3 then has to be 40 degrees. Intensity I3 then is equal to I2 times cosine squared of 40. I2 is then equal to I1 cosine squared of the angle difference between 1 and 2. So if I draw the picture, I look at the second polarizer, here's my 20 degrees. If I look at the first polarizer, it's at 40 degrees, so it's the angle difference between these two. This tells us that the angle is 70 degrees, so therefore I know what I2 is, which is I1 times cosine squared of 70 degrees. Now putting this all together, we get intensity I4 is then I4, I3 cosine of 40. But I3 is then I2 cosine of 40 squared, so I get two terms like that. And then if I look at I1 is only half the intensity, so then I get I naught times 1/2 cosine squared 40 times cosine squared 40 times cosine squared 70. If the initial intensity was 25 watts per meter squared, then I4 is 0.5 watts per meter squared. Problem 2. The radii of curvature of the surfaces of a thin converging meniscus lens are R1 equal to 12 centimeters, R2 equal to 28 centimeters. A. Compute the position and size of the image of an object in the form of an arrow 5 millimeters tall and 45 centimeters to the left of the lens. Is the image real or virtual, erect or inverted, enlarged or reduced? B. A converging mirror of radius 70 centimeters is placed 228 centimeters to the right of the converging lens. Find the position and size of the final image. Is the image real or virtual, erect and inverted, or enlarged or reduced? Draw a ray diagram showing the location of the final image. First thing that we got to do is we got to get the focal length of the lens. So I have R1 at 12, R2 at 28. So a converging lens is thicker in the middle, and therefore we must set up the radii correctly. So if I have the smaller radii on the outside and the larger on the inside, then you could see this is thicker. If I switch these around, you could see that the larger versus the smaller makes it thinner in the middle. Therefore, this is the one we want. So the smaller radii is 12, the larger one is 18 centimeters. Let's calculate the focal length. The left of the lens is the negative, to the right of the lens is positive. Let's calculate the focal length. Focal length is determined by the lens maker equation where R1 is positive 12 centimeters, R2 is positive 28 centimeters. So I'll get 1 over the focal length, gives me this, that I had R squared terms here, which is incorrect. That's correct now. So then I plug in my values and I get a focal length of 35 centimeters. Calculating image S1 prime. So here's my converging lens, f1 positive 35 centimeters. I have an object that's s1, which is 45 centimeters from the lens. So let's draw the ray diagram. I have ray number 1, ray number 2. They converge at this location here, so I can see that the image is going to be inverted, larger, and real since it's on the other side of the lens. Calculating the image distance S1 prime using the thin lens equation. Here's my equation here, so now I got to solve for S1 prime, then get an image distance S1 prime of 157.5 centimeters. Magnification of the first lens is then M1 equal to minus S1 prime over S1, which is minus 3.51 equals to M1. Calculating final image S2 prime. So I now have a converging mirror. It's 228 centimeters away from the lens, and it has a positive focal length of 35 centimeters. So when I look at this thing here, this thing is at 70 at this second focal point here, or 2F point, and this guy is going to be outside of this thing here. So when I draw the ray diagram for this image, it's going to look as follows. So the first ray is ray number 1, so it's parallel, reflects through the focal point, and then I need the one that goes through the middle of the mirror. So I need to set up an equal reflection point. So then I follow this back and then go back to here, and you can see that's where they cross. So the final image looks like it's erect, and it's going to be smaller than the image that produced it. For this object S2, I need S1 prime, which is 157.5 centimeters. I know the distance between these two is 228 centimeters, so therefore the new object is then 128 minus 157.5 centimeters, which gives me 70 centimeters. So now I got all the details here. Calculating the image distance S2 prime using the thin lens equation, I then get a distance of 70 centimeters. Magnification of the converging lens is M2 equals to minus S2 prime over S2, which gives me minus 70 over 70, which gives me a magnification of minus 1, which is equal to M2. Total magnification is capital of M total is M1 times M2, so I'm going to get minus 3.5 times minus 1, which gives me a positive 3.51 magnification. So what are the image characteristics? Note that this is to the left of the converging lens, so therefore it has to be a real image. It's erect and it's larger since its magnification is 3.5.